Nipkow and Thomas Sewell. It's approved Perl and Braun trees, and Tobias is going to give the talk.
Right. So for a little bit of light-hearted entertainment, Braun trees. So where does the name come from? Yep. Use the work. Yes. That wasn't the effect I wanted. I think I'm pressing the wrong button. Yep. Let's try that one again. Right. Yes, so the name comes from the student who originally came up with this data structure in the context of implementing Dijkstra's flexible arrays efficiently, that is with logarithmic access time. And it was very much in an imperative setting, and then later on people realized that it's actually quite a nice, cute functional data structure and has got nothing to do with imperative arrays. And it does support arrays and priority queues, and that's what I'm going to focus on in this talk. And the point is that if you look at the literature, then you see quite a bit of code, but you see very few proofs there, including some properties that I did not find obvious. And so our contribution is really sort of to provide the definitive reference for Braun trees if you're interested in the proofs as well as the code. So this is what the paper is about. Of course, I'm not going to show you the proofs. So what I'm talking about will be mainly the algorithms. So what are Braun trees? They are characterized, if they're binary trees, then they are characterized by the invariant that every node, the left subtree, must either have the same size as the right subtree or must be one bigger than the right subtree. And it has a nice consequence, namely that the size determines the shape. Once you know the size, you know the shape. And this is shown in the following diagram. So I will now enumerate the shapes of the Braun trees in increasing size. So this is obviously the Braun tree of shape of size 1. This is the one of size 2, 3, 4, 5, 6, 7, 8, 9, 10. And there are a couple of things you can already see, namely that all the time, if you increase the size of the Braun tree, it doesn't completely change its shape. You just add incrementally one more node to it. And you can also see that that all of them are almost complete. Only in the last line, at the lowest depth, nodes are missing. And if you look at the full tree, you can also see that all the even ones are on one side, the odd ones are on the other side. So it's got lots of nice properties. And now, how do you use this as an array? You need to index into it. How do you index into it? Well, you just replace, well, these are, just to make sure, these are not the contents of the nodes. These are the indices of the node. And so if you interpret the indices in binary, then it's just a try. And you can just reach any node using, for example here, using the bit pattern as a direction how to reach from the root the particular node that you're addressing, and 0 and 1 telling you whether to go left or right. So a couple of nice consequences. The invariant implies that the Braun trees are almost complete. That means they have optimal height with respect to their size, which means you have a logarithmic implementation of arrays indexed by the numbers 1 to n. So, but you have more than just normal arrays. You have these flexible arrays. So what do they give you? There you can add and remove elements at the high or the low end, one at a time. And it's pretty obvious you can do it easily at the high end. I showed you that when I incrementally constructed those trees, I just added one more element. But why can you also easily add and remove them at the low end? Let me show you for the add the function. So if you want to add the element x to this tree here, then x at the low end you want to add it. That means it should have index 1 afterwards, and everything else should be shifted. And so if it has index 1 afterwards, it should be the root of the tree. And then you have to insert the current root, and you have to insert it into one of the two subtrees. Obviously, you have to insert it into the subtree R, because if you insert it into the left subtree, that one gets too big. So you just insert it into the right subtree, and you swap subtrees, because by the re-indexing, the odd and the even ones are just swapped. And so this is the almost complete definition. Of course, there's a base case, but in all of my definitions on the slides, the base cases will be missing. And almost equally simple is the deletion at the low end. It's just, again, one traversal through one path and swapping subtrees. And the correctness proofs are quite straightforward. You have an abstraction function list that takes a tree into a list. It's a easy recursive definition that takes the lists from the subtrees and splices them alternately. And this is an n log n function. Later on, we'll be interested in a linear function to convert the tree into a list. But at the moment, this is just a correctness device and has no, I'm not intending to execute it, so the fact that it's n log n isn't really that important. So 4 algorithms on Braun trees, that's actually a variation on the title of a paper by Chris Okasaki, 3 algorithms on Braun trees. So what are the 3 algorithms? The first one is that you can compute the size of a Braun tree in log square time. So you don't need to go through the whole tree if you know that it's a Braun tree. You can also build a Braun tree with all the nodes having the same contents with n nodes in log n time, lots of sharing there. And you can convert a list into a tree in linear time. But it's only 3 algorithms, so what was missing there was the converse function that takes a tree and converts it back to a list in linear time. And the original straightforward attempt that you saw on one of the previous slides isn't linear. So this is the function that, this is the idea that underlies the direction from lists to trees. You do it layer by layer. So here you have your input elements. And if you have just x1, then of course it corresponds to that tree. Here the x's are really the elements and not the indices. And if 2 more elements come along, then they will get added to that tree like this. And if 4 more elements come along, or some sub sequence of those 4 elements, some initial fragment, then they would get added as well. Now it looks a bit simplistic down here, up here, but here now you can see things aren't completely trivial because here you get a different order than you have here. So there is some shuffling that has to be done in the right manner. And so, but what you can see, somehow you take the input in chunks of powers of 2. And that's, in the end, the code that we verified when I write inspired by Okasaki. The basic idea is there that they're exactly the same, but the code looks quite different from Okasaki's code. And I'm not going to explain the code to you, but you can see all these takes and drops of powers of 2 that chops up things and then somehow combines them in the right manner. And it is indeed what may not be immediately obviously in linear time algorithm. In the other direction, let's look at a part of the tree. This is if you, of course, there are more nodes up here, and now I'm reverting back to the index notation. So this is the tree as we have seen it, but you can see also if you want to convert that back into a list, of course, a list in the order of the indices, then the order of the indices here is wrong. So you have to swap them here. And then something very nice happens when you've done that. Then you can see, okay, when if you want to turn that into a list, you first take all the roots, then you take all the right subtrees from 8 to 11, and then you take all the left subtrees from 12 to 15, and that's the order which will give you the correct projection of the tree into a list. And then in the end, that's the recursive function, and all you have to do to show that it's correct and has the right complexity. And the fact that it's correct, that's the main, sort of the main ingredient that we provide. Some notions that allow us to express this correctness. So the key one is here, this Braun list that establishes a correspondence between a Braun tree and a list of elements. And I'm not going to go into it, but once you have those notions, then the proofs are reasonably straightforward, but coming up with those notions is the key ingredient there. And so these are the main theorems about the Braun's function that, given a list of elements, gives you a back list of trees, and the list prime function given the list of tree gives you back a list of elements, and they do use those additional technical notions that I introduced. Now, trees are one thing, search trees, arrays, priority queues are another popular data structure, and Braun trees are a good realization for that. So, of course, trees realizing priority queues means you're using a heap where the smallest element is at the root and the smaller one, the bigger one's below. And how do you maintain this heap if it's a Braun tree? Well, the key operation is the del-min operation that removes the element and then is left with two trees that have to be combined. I'm going to show you two similar but somehow slightly different log n implementations for this del-min operation. The first one comes from Larry Paulson's ML book, where without proof he presents the algorithms and actually credits them to Okasaki personal communication. And the del-min function is similar to heap one step in the heap sort algorithm, and it looks like this. So you wanted to remove the x here from a node LXR. So of course then you have to in the end create a new tree. You have to replace x by something, and since L is the possibly bigger subtree, you remove an element from L, namely the leftmost element. That's what you do here. Then you get this leftmost element y and what's the remainder of this L, and then you call the sift down function, which recombines the right subtree, the leftover of the left subtree, and this function, this element that you've pulled out. And the sift down function, I don't think you want to read the details. Let me just show you two examples. Sift down, if you have two heaps and an element in the middle, and the element in the middle is really smaller than the two heaps, then you just create a new node with that element in the middle. If, on the other hand, you have an element that's bigger, at least bigger than one of the two heaps, you have to let it sift down further. So you take the smaller, the root of the smaller heap, you put it in the middle. One heap goes unchanged, and in the other heap, you let the element in the middle sift down. There's a slightly different implementation by Filliâtre, which he verified in Y3, and that works like this. It says, okay, you want to remove the middle element, why don't you just merge those trees? So he has a recursive merge function. Again, we don't want to look at all the details, but let's look at the two characteristic cases. This is the nice case. If you merge two trees, and on the left tree, the one that's supposedly bigger, you have the smaller element, then you just pull it out to make it the root, and then you merge the subtrees over here and you swap. But on the other hand, you run into a problem if you're trying to merge these two trees, because now if you pull the one out, this tree here, this is part of the right part of a Braun tree, will get, if you're unlucky, two smaller than this one, so you're no longer a Braun tree. And so you can't do it like the way you've done it here. And then what Filliâtre says, okay, well then you take from the bigger tree, you extract an element and a remainder tree, and then you call a replace min function, and you replace this element that you've pulled out for the minimum element in there. And if you stay long enough at this, then it turns out this is just another way of saying sift down of left 2, 9, and right 2. So in the end, the algorithms are almost the same, except Filliâtre optimizes a little bit. He tries to get away without this at the top of the tree, and therefore, I guess, has a little bit of an advantage. Priority queues, of course, can be used for sorting. It doesn't matter what the priority queues are. So that's a standard idea. You turn the list into a priority queue, and then you extract the elements from the list one by one and get a sorted list. So how is this done with Braun trees? So in the end, you get an n log n algorithm if you do it halfway decently. We looked at two implementations. One is again by Paulson, and it's similar to the array-based heap sort, so I'm not going to go into the details. The other one is by a very unknown paper by Guttman and colleagues. And they do something which strikes me sort of how inefficient can you do it and still get an n log n algorithm? That's the kind of approach here. So the first step, if you do it cleverly, you take the list and convert it into a Braun tree. You can do that in linear time. We know that. But they don't bother to do that. They say, well, they don't explicitly say so, but essentially what they do is they just do this. They fold the insert function that inserts one element after the other into the Braun tree, and they fold that over the input list, and then you get an n log n algorithm already for this step, but it doesn't bother you because overall you're just happy with n log n. So that's the first place where they lose. And the second one where they do something surprising is the extraction. So they, how do you extract from a Braun tree the elements in order? Of course, you start with the smallest one, then you merge the two subtrees, and you then recursively extract them. But what they do with the merge function, they don't do anything complicated. They essentially do things naively without looking at the code. It turns out that this merge does not preserve the Braun invariant. And so first I was a bit shocked and thought, well, that's really bad. Doesn't that hit their performance? But no, it doesn't, because merge still runs in time proportion to the height of the heap, and it can't increase the height. So it'll, in the worst case, really have n log n times the logarithm of the initial n. Whereas normally, if you do it cleverly, then of course the heap gets lower and lower, and you again your performance is better. So this is, I think, sort of on the border what you can do with n log n and still get away with it, although it's not terribly efficient. So what's the conclusion of all of this? There are lots of cute and tricky algorithms on Braun trees, and we added some of the missing pieces, both in terms of code and in terms of proofs, and in particular the proofs because they were somewhat lacking in the literature. And that brings me to the end.
We have time for a few questions.
So you've given the algorithms. One of them is new, and you've done the functional correctness proofs. Did you do also the complexity proofs?
Yes. In a very naive manner, we just wrote down recursive complex time functions and then proved things about them.
Okay, thank you.
Thank you. That was a lot of fun. I'm guessing that these would make good exercises in whatever proof assistant you like. I happen to like Agda, so. Yep. Cool. And you mentioned you did the complexity proofs. Do you have a formal link to show that these are complexity, or you just looked at, you said, okay, here's the complexity function, and then you proved properties of that? Yes.
I mean, the complexity function is essentially an abstract interpretation of the original function that computes with numbers rather than that doesn't compute, that computes the number as the output rather than the list or something. You could, in another paper, I had actually done it more in a more disciplined manner, that I wrote one function that has a time monad and computes the time in the background, and then in the end you split it up into two functions to do the separate proofs. But I didn't bother here. Yeah, but you could be done.
Okay, very nice. Nice work. Thanks.
Thank you, Phil.
Other questions?
Yeah. Two quick questions. If there is a implementation, where the type check can preserve the Braun invariant, and the second kind of relate to that. When you're doing this manipulation, and some of them you say you show some algorithms which do not preserve Braun invariant during the processing. Is it possible to do it with preserving Braun invariant, or if there's you will lose performance?
I didn't understand the first question. I get the impression that you're thinking in terms of making the invariant part of the type, yes. Which we didn't. The invariant is just a predicate on the tree, and so I'm sure you could also do it with a dependently typed system. I don't think the the difference would be too big, although I don't, of course it depends on the automation in the dependently typed framework. And the performance, I think the performance should increase if you don't, so if you go back to this sorting function and you do the naive version of merge, then you can, the size of your Braun tree can degrade, and I think it would, I'm not quite sure. I think it should, intuitively, I think it should improve if you preserve the invariant, but I'd have to look at it again. Yeah.
Any other question? All right, let's thank the speaker again.